Welcome back. We have seen that the pointwise convergence of the Fourier series is a difficult thing to handle at the present time. So, one can ask the question that if we have the partial sum of this is minus n to n f hat n e to the power I n x, does it converge to f in some other way other than the pointwise convergence? So, what can be the possibility of the convergence, whether it converges in mean or not? So, what we would like to see that whether this S n f of x, it is a trigonometric polynomial. So, this is integrable minus of f of x to the power dx, whether this goes to 0 as n goes to infinity. Okay. So, in order to do that, so let us recall some of the facts what we have seen in our linear algebra course earlier, namely the inner product, in the space of Riemann integrable function minus pi to pi. So, this space consists of all 2 pi periodic Riemann integrable function. So, it does not matter whether I am taking minus pi to pi or 0 to 2 pi. Okay. So, let us define, let f g both are Riemann integrable 2 pi periodic function, and we define the inner product f inner product g. This is equal to 1 over 2 pi minus pi to pi f of x g of x bar dx. Here we are allowing ourselves to consider complex valued function. So, if it is not a real valued function, then it is nothing but integral minus pi to pi f of x g of x dx. So, as in order to show that this is an inner product, what we need to show from our linear algebra course, f 1 plus f 2 comma g, this by the linearity of the integral, it is easily we can see that this is f 1 inner product g plus f 2 inner product g. Similarly, f, it is also additive in the second coordinate. This is f g 1 plus f g 2, and if alpha is a scalar, then what we do, alpha f of g, this is equal to alpha times f comma g, and if beta is a complex number scalar, then this is going to be in the second coordinate, this is beta bar f of g. It is linear in the first coordinate and which is skew linear in the second coordinate. So, now, so as a consequence of that, what we get is that this alpha f 1 plus f 2 beta g 1 plus g 2, this is going to be alpha beta bar f 1 g 1 plus alpha beta bar f 1 G2 plus alpha beta bar F2 G1 plus alpha beta bar F2 G2. Okay. So, now what we can see is that if I take f inner product with f, this is equal to 1 by 2 pi minus pi to pi f of x into f of x bar, that will be mod of f of x square dx, which is greater or equal to 0. Now, if f is equal to 0, then this will imply that f this is equal to 0. However, if f is equal to inner product of f with f is equal to 0, we cannot conclude that f is equal to 0, because we know that there are non-zero Riemann integrable function whose integral is 0. Not only that, non-zero, non-negative, because at one point if we are changing the value of f, you consider f to be 0 everywhere except at one point and give certain value, then that integral is going to be 0. However, f as a function may not be equal to 0. However, if f is a continuous function, then f is equal to 0 will imply that f is equal to 0. That is as we can see that if f is not equal to 0, which means mod f square is a continuous function, is not equal to 0 at some x naught, let us say, then suppose I have minus pi to pi here and x naught is here, it is taking a positive value, then I can always find a neighborhood of x naught in which mod of f of x naught is not equal to 0. Hence, integral mod of f of x square, which is greater, suppose this neighborhood, let me call this as I, then f is greater or equal to 1 by 2 pi integral over I mod of f of x square dx, and which is positive, which is a contradiction. Therefore, f has to be equal to 0 provided f is a continuous function. Okay. So, this if we look at, if we denote two is equal to, then square. If I am denoting this, then this I will call the norm of f, and this norm is going to satisfy for any Riemann integrable 2 pi periodic Riemann integrable function. This is greater or equal to 0, and if f is equal to 0, then norm of f 2 is equal to 0. Now, if f is a continuous function, then norm of f is equal to 0 will imply that f is equal to 0, that is one thing. Second thing is easily one can see that f plus okay, if I take alpha and hit that with f, then if I am doing this, then this is going to be mod of alpha norm of f of 2 norm, because alpha square and then this is norm of f square. So, mod alpha is going to come out of it. Third is that norm of f plus g is less or equal to norm of f f 2 plus norm of. So, this requires a little bit of argument for that. So, for the time being, let us just assume this is what we are going to get. Okay. So, now this is what is our norm. As you can see that this norm, if we compare this inner product in R n, then as you can see the norm what we are defining it here, this is essentially nothing but the Euclidean metric norm of x, which is means the distance from 0 to the vector x. This is analog to that, and which provided us a notion of certain distance in the space of Riemann integrable function. So, now one of the very interesting thing here is that the Cauchy-Schwarz inequality. So, which states that mod of f g is lesser equal to norm of f 2 norm of g of 2 norm. So, now before proving this, so what one can see that if f is Riemann integrable and norm of f 2 is equal to 0, then what we can say is that we may not be able to say that f is 0 at every point. However, as we have seen that at 1 point, 2 point, if f is not 0, that is not very serious. So, what the result it says is that if this is equal to 0, then there exists a set E contained in minus pi to pi such that f of x is equal to 0 for all x belongs to the E complement, and then one can say that what is going to be the size of this set E, which essentially says is that the E can be, now if I take the infimum of all those summation of the length of the interval I n such that E is contained in I union of n, countable union of n of I n. So, now E is such a small set that if I take any E and cover it by the countable union of intervals and I take their sum of each individual interval, then this is going to be 0. That means it is negligible. In fancy word we say that f is equal to 0 almost everywhere. As a matter of fact, this is if and only if condition that if f is Riemann integrable, then in this case we will say that the E has major 0. So, now it says that if f is Riemann integrable, then f is continuous almost everywhere, if and only if it is continuous almost everywhere. Apart from the set, with a very small set, f is continuous. Once we have that, then it is easy to see that if f is a continuous function, non-negative function whose integral is 0 and continuous, then f is 0. So, what we can say is that f here is equal to 0 almost everywhere. but we are not going to use that much. So, this essentially suggests that because you remember that when we are talking about the Riemann integral, then when we are taking the partition, then we are choosing any arbitrary points and we are constructing our rectangle, and we have the freedom to choose any arbitrary point. However close these 2 points can be, their functional value will be close provided f is nearly continuous. Otherwise, that is the reason that when we look at the indicator function of rationals, then which oscillates 1 or 0, in that case that is not Riemann integrable. So, okay, so we can assume here to the proof. So, norm of f and norm of g, they are not 0. If one of them 0, then we know that the inner product is 0. So, f is 0, therefore, the inner product is going to be 0. So, the inequality satisfies. So, this is a trivial inequality for any two non-negative number a b greater or equal to 0, 2 a b is less or equal to a square plus b square, that is trivial because a minus b whole square is greater or equal to 0. So, by using this, what we can see is that f of x, g of x, this is equal to square root of norm of g by square root of norm of f mod of f theta f x into square root of norm of f, all these are two norms, because we are assuming that both norm f and norm g, they are non-zero. Now, take this as a and this as b, therefore, this is less or equal to 1/2 of norm of g 2 by norm of f 2 into mod of f of x square plus square. Now, I integrate both the sides. So, this is okay 1 by 2 pi minus pi to pi f of x g x bar dx. Now, this is mod, this is less or equal to 1 by 2 pi minus pi to pi mod of f of x mod of g of x dx. Now, we apply this inequality, this is true for each x. Therefore, if we by applying this inequality, what you are going to get is that this 1 by 2 pi. So, 1 by 1/2 factor will come out, and in the first integral this is minus pi to pi, then norm g 2 by norm of f 2 mod of f of x square dx plus 1/2 of this is what, because these are all scalar, they are going to come out of the integral. So, now this is nothing but if I take the factor of 1 by 2 pi there. So, this is 1 by 2 norm of g of 2 by norm of f2 into this one is nothing but square plus 1 by 2 . So, therefore, this is nothing but norm of f into norm of g. Now, as you can see, the equality is going to occur when this equality is going to happen. Therefore, the a square plus b square is equal to 2ab. Therefore, a is equal to b. So, that is what is the equality. Okay. So, now as we have seen in our linear algebra course, inner product actually gives the notion of extends the notion of angles from R n to an inner product space. So, in the similar way we can say that f and g are orthogonal if, that is, we will write it f is orthogonal to g if inner product of f g is equal to 0, exactly like the dot product. So, now what are the example over here? So, let us see one of our favorite example is going to be e to the power I n x for n varies over z. If I am defining f n to be this, then as you can see, if n is not equal to m, then f n f m, this is equal to 1 by 2 pi minus pi to pi e to the power I n x into e to the power minus of I m x dx, which is what we have seen 0. So, this is one of the most important property of e to the power I n x. So, they essentially they are orthogonal, it is an orthogonal family. So, and also in this case the f n square is nothing but going to be 1. So, now another example you can take is that if you take f n of x, this is equal to cos n x, then what you are going to get is that this is going to give you an orthogonal family, let us say in 0 to pi, let us say. Now, then the inner product I will define to be integral from 0 to pi f of x g of x bar. Then as you can calculate that if n is not equal to m, then this is going to give you 0. So, this is orthonormal family is what? A family of functions phi n of function is said to be orthonormal if inner product of phi n phi m, this is equal to 0 if n is not equal to m and 1 if n is equal to m. As you can see that if we have a orthogonal family, then by defining let phi n be an orthogonal family, that is inner product of phi n phi m, this is equal to 0 if n is not equal to m. So, now if we take let psi n, this is equal to phi n by norm of phi n, provided if norm of phi n is not equal to 0, then we can divide it by this. Then as you can see that psi n psi m inner product, all this phi n norm and phi m norm, they are scalars, we can pull this out from the integral, which is equal to 0 if n is not equal to m. Now, if n is equal to m, then in this case this is phi n, this is equal to norm of phi n square, and in the below you have norm of phi n square. So, n equal to, so this is going to be 1 if n is equal to m, which means if we are provided with orthogonal family, then we can normalize this and make that to be orthonormal. Okay. So, another example of the orthogonal functions, let f then we have S and F. Let P of x is equal to summation over alpha n e to the power I n x, where mod of alpha lesser equal to n, which means it is, I take P to be a trigonometric polynomial of degree lesser equal to n. Now, let us see f minus of S n f, that is the most important object we would like to know about this along with this P. Then this is, we will just write down the definition. This is f of x minus S n f is mod n lesser equal to n f hat of n e to the power I n x, and then summation over mod k lesser equal to n alpha k bar e to the power minus of I k x dx, that is p x bar. Now, this you can see that by the linearity of this, alpha k bar e to the power minus of I k x dx minus 1 by 2 pi, and this is a finite, both are finite sum, we can pull this both the sums outside the integral, and what we are, and f hat of n is scalar, alpha k bar left with e to the power I n x into e to the power minus of I k x dx. So, in the next lecture we will finish this computation and we will see that f minus of S n is orthogonal to every trigonometric polynomial with degree lesser equal to n. Thank you.